Okay. Next video, and this is going to bring us to an end of your first part of previewing. The next part of it, you guys, I'll have you guys do when we get back from vacation. Okay. So now that we've discussed discrete random variables, we're going to move on to continuous random variables. Okay. So discrete random variables commonly arise from situations that involve counting something. Okay. Situations that involve measuring something will often be more like continuous random variables. Okay, so why I suggested something like weight in the last video. Okay, that's more of a measurement. It's not a count. That would be continuous. It's not discrete. You can have part of a pound. You can't have part of a person. Okay, so you cannot assign probabilities to each individual value of x. There are infinitely many possible values, okay, which means we might need a certain model to help us out here. Going to be the normal model, but we'll get there in a second. So a continuous random variable x takes on all values in an interval of numbers. The probability distribution of x is described by a density curve. The probability of any event is the area under the curve, under the density curve, and above the values of x that make up the event. So the probability model of a discrete random variable x assigns a probability between 0 and 1 to each possible value of x. All continuous random variable y has infinitely many possible values. All continuous probability models assign probability 0 to every individual outcome. Only intervals of values have positive probabilities. Okay, so in situations like this, we use a different way of assigning probabilities directly to events, such as areas under a density curve. Okay, any density curve has an area of exactly 1 underneath it, corresponding to the total probability being 1. Okay, so let's take a look at an example, and we will be done with this. Okay, so because it's continuous, and because we saw that these are based on a density curve, or that everything under a density curve totals 1, just like your probability, we're able to use a density curve, but often we'll use a common one, which is our normal curve. Okay, so the heights, young women's heights. So the heights of young women closely follow the normal distribution, with mean 64 inches and standard deviation 2.7 inches. Okay. This is a distribution for a large set of data. Now we're going to choose one woman at random. We're going to call her height Y. So if we repeat the random choice very many times, the distribution of values of Y is the same normal distribution that describes the heights of all young women. So we're going to define Y as being the height of a randomly chosen young woman. We're going to find the probability that the chosen woman is between 68 and 70 inches tall. So what's the probability that a randomly chosen young woman has height between 68 and 70 inches? So it's a normal curve, so we know it looks symmetrical, peaked at the mean, okay? We need to find the probability between 68 and 70, okay? So we could either use z-scores, so find what the z-score is for 68 and the z-score is for 70, okay? And then we can use either our calculators or a table, but we'll use our calculators to find that the probability here would be 0.0562. That's not typically how we would have done it, okay? The second that we know that it's a normal distribution, it's a normal distribution with a mean of 64 and a standard deviation of 2.7, we have a habit of putting it into our calculators. So we would do norm CDF, our lower our lower bound would be the 68, our upper bound would be that 70, the mean would be 64, and our standard deviation 2.7. And putting it into the calculator would give us 0.0561, which is a little bit more exact, but it's about the same. So there is about a 5.6% chance that that a randomly chosen young woman has a height between 68 and 70 inches. Okay, and that is it for this video.